Okay, so the second and last speaker of this session, and indeed of the workshop, is Radu Cimpeanu from the University of Warwick. And shall I let you say your title?
Of course. Thank you very much, Mark. And yeah, it's been lovely being here both for the summer school last week and for the workshop now. I think the only sad thing is it's going to be over, the workshop itself, but luckily we get to continue a bit with the research retreat. And yeah, it's been a lovely few days already. I decided I'm going to be brave, and instead of talking about interfacial flows with 2 fluids, I'm going to go for 3 fluids, hence the title. And I wanted to tell you the story as a configuration of 3 different problems as well. So I'll get to it in a second. But before that, to set the stage a little bit, I quite enjoy the type of problems where you get to combine different techniques, often the type of nonlinear problems where analytical methods, usually something to do with asymptotics, can combine nicely with the high fidelity simulation type of techniques to kind of make a more cohesive whole out of the 2 parts. And the way I like to split them into kind of 2 different classes of problems is such that on the one hand you have difficult problems that there's enough violent nonlinear dynamics happening on its own that you want to understand what is happening. And on the other side, there are gentler problems. Think about contexts in microfluidics and so on, where things are quite slow and gentle, and you need to get things going, and often that involves interacting with external forcing and so on in interesting ways. So I owe much of what I'm going to talk about to the research group, and in particular to Dr. Benjamin Fudge, because all the next 3 problems I'm going to speak about are 3 chapters of his thesis. And he's been working in the Oxford Fluids Laboratory in Oxford in the engineering department for the past 5 years or so now in this context on a series of problems that had to do with impact problems in particular. The other person you may recognize in this slide is Oscar from last week in the summer school, and maybe also from Susanna's presentation earlier this week, who's done some very nice work on control theoretical side for the other branch of projects I've talked about. But yes, today we're basically going to focus on the higher Reynolds number side of the spectrum. And with that in mind, I wanted to set the stage with kind of when I started historically thinking about this problem. So around 2015 is roughly when I was wrapping up my PhD stage. And it was also the time that this beautiful paper from the Johns Hopkins group came about. It was about impact onto thin liquid films of oil. And it was motivated by the fact that that was a period with a lot of environmental disasters, like think thin films of oil after an oil spill like the Deepwater Horizon disaster. And in many of those cases, the other bad thing happening was those were tropical areas with a lot of storms. So you got intensive rainfall on top of an oil slick on top of the ocean. And the primary issue actually seemed to be that because of the aerosolized oil droplets coming out into the atmosphere, the wind was sweeping them away, they're light, and they were being carried tens of kilometers and being a key contributor to shoreline pollution. So we were interested both in terms of how does the impact take place and how do these secondary droplets form, but also what happens to their destiny a bit later on, kind of in a multi-scale way. The only reason I made this slide particularly rich, apart from telling you the story, is also to emphasize this was a wonderful experimental paper that touched on so many regimes. It was quite inspirational to look at. The other thing is the amount of data, the amount of oil thicknesses, impact speeds, and so on was such that you could really kind of pick your poison, if you will, in terms of where in the problem space you want to operate. The sad thing, kind of looking back, is that we treated this as the type of problem that, as I was transitioning to my postdoctoral years, seemed like a nice one to set the next stage of one's career going. And I'm happy to say I'm still thinking about it 10 years on, and we've had discussions about it this week analytically and computationally as well. So yeah, it's been a really good pick from a certain perspective. I mentioned that we were also interested in what happens to the droplets afterwards. I had a really nice student at Warwick as part of our undergraduate research program, and she had a knack for drawing beautiful pictures as well. So we were looking at the secondary drop trajectory side, and this picture really kind of paints my previous description much more nicely, which is if you do have oil-covered surfaces and you do have a splashing event on top of them, essentially you need to understand the 3-phase impact problem. You need to understand how a water droplet interacts with an oil film in otherwise a gaseous environment. So this kind of motivated the first part of this process. The other historical paper I wanted to touch upon, and it's only 12 years old, so not that historical, but it's a beautiful study from the physics of fluid groups in Twente. And this is actually a 2-phase flow paper. And what the point of interest here was, as a droplet impacts a liquid pool of the same liquid, so water in this case, you have a gas film that's stuck between them, as we well know. And this allows you to take measurements with clever experimental techniques of where it is. So it allows you, if you do want to monitor the velocity of this interface between them for sufficiently early times, this gives you a handle into this. And it turns out that for a class of different fluids, be it water or silicone oils, there is a classical result that basically this interface moves at half the speed of the impacting velocity. So for this kind of class of regimes where you initially get the pool to deform and coalescence eventually happens, but the gas film is maintained between the two, this half represents a good reference velocity for one I'm going to talk about next, because the key target for ourselves will be what happens to this velocity if you have the third fluid in. And this was a really nice result because it then impacted a number of other beautiful studies. Marie-Jean talked earlier about a whole host of nice problems, and another one I quite liked from about 5 years ago was called To Split or Not to Split, which considered the fate of this gas film entrapped between them and whether it splits into a bubble ring or not, and results from this paper with the half velocity were quite relevant there as well. So these are, I think, what we need as the most important two ingredients. And with that in mind, I'll tell you a little bit about kind of what we set out to do. So I mentioned we wanted to figure out what happens with interfacial velocity, and we wanted to do so within a class of problems, within a parameter regime that's quite rich, because oils often come with different viscosities and different properties, and it was important that our results have some sort of generalizability. And for that, we set up a team that was actually quite extensive. So I mentioned Ben, who's the star of this work, having done both experimental and computational studies. He was supervised by Alfonso and myself, and we had really good help on the experimental side from Rafael Castrejon-Pita's group now in UCL as well, and Arnaud Anfoyac at the Sorbonne University in Paris also helped us with some of the modeling elements. Ultimately, what we wanted was that our results still maintain some level of compactness, if you will, in the sense that we wanted them to be usable and not to have to rely on long and difficult computations for every iteration of them. So in an ideal world, we really wanted a good formula to come out of this as well. So I'll start by describing each of the components for the first project. The experiments were really nicely captured. So what you see here is the twin camera setup that we had. We wanted to have a glimpse of the droplet as it impacted the top of the pool, and there was a camera pointing from the bottom to see the bottom of the pool deforming as well. We used 3 types of fluids for this experimental series. So, well, 4. Water, but water is not nice to work with if you do experiments because it's easy to contaminate. We used water-glycerol mixtures, which are a bit better. Then there's a fluid called fluorinert, and we used FC40 and FC770 for those who know fluorinert. It's a really cool fluid because it's chemically and thermally stable. It's very resistant to contaminants, which is nice, and it has a series of properties that make it great, apart from it being, I think, quite expensive, or in general, it's not your commonplace go to the supermarket type of fluid. But the other one that will come in handy later is silicone oils, and Ben in his lab had set up a series of little containers with silicone oils going from 1 centistokes to 1,000,000 centistokes. 1 centistoke is about the viscosity of water. So the reason I'm telling you these details is particularly for splashing, fluorinert has the nice property that it's got low surface tension coefficient, high density. So if you want to do splashing, it's a great fluid to work with. And then if you want to play with viscosities and study oil type problems, the fact that you can go from 1 to 1,000,000 is a nice kind of range to cover. And all of these are immiscible, so you have an actual interface between them. And we were trying to measure as much as we could experimentally with this setup, so I'll show you a typical movie that comes out. This is from the bottom part. So I'm sorry that the lighting is not great, but what you see basically is the bottom of the drop/top of the pool in this case. And the other noticeable feature is that there is a little bubble entrapped underneath this moving downwards. So it's the speed of this front that we were interested in modeling. The other ingredient on the computational side is we've heard quite a bit about Basilisk over this week. I will not belabor the point, but it's a wonderful tool to do the type of computations that require topological changes in particular. So if you do have problems that involve coalescence, splashing, and so on, I think it's a really reliable tool that's been very useful to the community. So we're very grateful for all the development that's been done in it. The type of equations you solve are the full set of Navier-Stokes equations in a one fluid formulation. So there's this color function that lives behind all of this, that if you have a two fluid system, you'd have, say, 1 in your dominant fluid and 0 in your subdominant fluid, typically liquid and gas, and you can transition between densities and viscosities in particular way, and you deconstruct and reconstruct the interface at every time step using information from the updated velocity field. This is kind of the standard setup if you have a more typical two-phase flow problem. If you have three phases, I'm happy to tell you there's actually been a burst of activity happening in the past year or so. I know of at least 4 or 5 groups who have done fantastic work in it. So I decided, kind of as a throwback to the summer school, to show you where they are in case you're ever interested. So the one we are using, and I think his name was mentioned in Marijan's talk before, Cesari has developed the first that I'm aware of library for three-phase flow modeling. By the way, in this one, you do get choices as to how many color functions you use now. You no longer have one. You can model it using 2, 3. You can have various clever formulations. But this was the first one that I knew that could handle a little bit of everything. Then the physics of fluids group through Vatsal Sanjay's work has another library. So what I'm showing you above is all the sandboxes from the users in Bangladesh who have contributed to their own spaces. And here also you get to see, some of the formulations of how you generalize that color function law to contain a third fluid. So all of these you can, plug and play, and they pertain to various interesting problems. Vatsal's case does not work with triple contact lines. However, it deals very nicely with problems that involve precursor films or covering droplets or bubbles or other structures. The other really nice piece of work I know comes from Ladix, from École Polytechnique, and Christophe Josserand has co-supervised this work of Pierre-Antoine Maes, who's defended his thesis just in January this year. And this is nice. Actually, I took an excerpt out of Pierre-Antoine's work because it's a really good description in French for the setup for the interfacial flows. But the point here is you see the different way of formulating it using either 2 interfaces or 3 different interfaces. And there are a number of subtleties also on how you design things like the advection schemes around this. So this thesis was a really nice body of work that robustly tested everything. And the final one that I was aware of, and courtesy of Stefan Zaleski, who was here earlier in the week, this paper just came out a few months ago. And what happens in this particular case, it's another robust algorithm that, rather than using, for those of you who know volume of fluid methods, quite often at the level of the cells, you use something called PLIC as an algorithm. It stands for piecewise linear interfacial construction, and it's code for me saying that it's actually discontinuous discretely at the level of each cell. And then you put them together through interfacial conditions and various algorithmic features. In this case, in Stefan's work and their colleagues, they used a smoothing procedure close to the triple contact point that allowed the algorithm to work directly on a continuous interface that made it quite nice to work with in both 2D and 3D. So everything I've just told you about, maybe apart from the library of Cesari, who is now 3-4 years old now, everything else is, very, very recent. So it's been nice to have a variety of algorithms that have kind of built towards studying different structures. I'm a computational specialist, so I hope you've indulged me in this little journey. But the point is, if you want to know more, I can tell you a lot more about both the experimental and computational side. I was just keen to kind of give you the insider's perspective. Now, if we jump onto results, qualitatively, what do we see for our target problem? So what I'm having here is a droplet impacting a liquid pool of, say, oil, something different. And you're seeing experimental snapshots on the left-hand side, numerical ones on the right-hand side, or interfaces on top, plugged on top of the experimental image. All in all, we were quite encouraged initially because we had pretty good agreement. And we could actually see decent, I forgot to show you the nice simulation movie, decent agreement. And to do this, it was necessary to basically have a nice adaptive refinement strategy around the interface shape and things like changes in the magnitude of the velocity field or the vorticity. You'll recognize this little bubble that appeared in the experiment as well. But what we were really after, I'll start it again, was the velocity of this interface, as I mentioned. So actually, in this case, it's nice because the bubble detaches and you can ignore it from a certain point onwards. But in many cases, the bubble does get stuck near the interface, and Ben devised a few nice algorithms to basically take care of this and make sure that the measurement is consistent throughout the batch of simulations. Great. how do we model this? So I've mentioned experiments, simulations. We want to do a bit of mathematical modeling as well. And you can take a relatively simple but powerful energetic argument. You can start off from the fact that the droplet comes in with a certain kinetic energy. And if you make a series of assumptions about what happens post-impact, so the region of interest for the drop itself is going to be hemispherical. You can confine the action in the pool to either a cylinder or a radial field. Both would work quite nicely. And the fact that there is a common interface between them, you can then analyze the post-impact energies and equate them. And in doing so, you can start deriving the key building blocks here. So I mentioned that you have a few choices, and there's been a few previous studies that have helped us along as well. So with this in mind, if we introduce now the suitable ratios, because unlike in previous problems, we have to take care of the fact that the pool has different densities and viscosities. If we start from the density, because this is the first one that appeared, you can come up with the interface velocity, which is the ratio of the post-impact velocity to the pre-impact velocity, of taking this type of formula, which you'll notice if your density ratio is 1, this is precisely the 1/2 that was known from the literature before. So this was good news. And then if you try to introduce viscous dissipation as well, so you have a new contributor to the energy landscape, you can do so, and you have to use a scaling factor, a coefficient in this case, and you'll get to derive, following the introduction of the viscosity ratio, a law that now includes both density ratio and viscosity ratio and the Reynolds number based on the droplet formulation. Because this equation was quite central to Ben's work, this was the first bit, but it'll affect the 2 other problems I'm going to tell you about. Within his thesis, we call this the fudge equation, and because it has 1 factor, we just call that the factor. And, yeah, if you're curious about it, it tended to be about 20 or so. You can actually put a prefactor, if you so choose to, in front of the density as well. And if you want to do a 2-parameter fit, it turns out that the best value for it is about 2.8. We thought that was overkill, so for us the 1-parameter situation worked nicely. But I'll show you the results with the other one as well. So if you use this expression and kind of compare it with the experimental measurements and with the DNS results, do you get anything that's intuitively interesting and robust? And the answer is yes. So comparing this to the hypothetical 1/2 line, this picture includes the predictive formula in continuous or dashed lines. So this is where I mentioned we have a 1-parameter or a 2-parameter fit, but honestly they're quite indistinguishable, so we can just focus on the one of them. Some of the symbols in green are experiments, and many of the other symbols in color are the DNS results. And what you see is that if the density, this is the ratio between the pool and the drop, becomes higher, the velocity of the interface becomes lower because it's more difficult for the droplet to penetrate inside of the film, and the converse happens on the other side. But it was interesting to note that the variation happens from about 0.2 to about 0.8, so we've unlocked quite a large number of velocities in this case that were kind of beyond the typical half value. The other thing you can do, of course, is then play with the viscosity ratio, so I've changed the image in the meantime. And I guess the interesting feature here is the plateauing. So it turns out that if the viscosity of the pool becomes lower than the viscosity of the drop meets relatively little resistance. So in that case, you get a saturation of this value. This is where you start seeing the 2-parameter version starting to work a bit better. But by and large, I think we were quite happy with the level of agreement, so we could take some heart from that. Great. That was problem 1. The other 2 are shorter, don't worry. Problem 2 has to do with even higher speed impact, so it's splashing in this case. It's taking us closer to our application, and we use the same type of toolkit, slightly different camera setup, slightly different adaptivity strategy because it's a more violent flow. But you see again qualitatively, now you get features that are a bit more violent in the sense that you get vertical roll-up structures, you may get jets starting to detach, droplets starting to form. I should have mentioned from the beginning that the simulations are axisymmetric, and if you want to design splashing type things, quite often splashing may happen non-axisymmetrically, which is actually usually the case. So there are limitations to be noted, but you'll see kind of where we're trying to take this. And in particular, I want to spend a bit of time on this figure. So what we're plotting here are all the experiments bended. Each one of them is a symbol, and stuff that doesn't splash is in red, and cases that do splash are in blue. There's one line here that I mentioned is theory, and I'll spend the next 3-4 slides telling you about what that is in a second. And otherwise, what we see are basically fairly clear trend lines as to when we can expect splashing and not splashing, with the surprising feature that for a viscosity ratio between the pool and the drop of about 30 or so, we get a situation in which we seem to get no splashes. We didn't get any splashes in the lab. Ben climbed to the second story of the building, I think, or the lab, to try to release the droplet, because the higher you release it, the better. We tried it with simulations. It didn't splash, but that was my caveat, that because it's a non-axisymmetric feature, we were unlikely to see it. But as far as we could tell, this was an interesting regime where splashing is very difficult. I'll come back to that in a few slides' time, but if you want as a homework to think about in the meantime, try to rationalize the situation a bit. Why do you think that happens? Why do you think behavior-wise, physically, you get this type of scenario? And why does it happen at this intermediate range of kind of viscosities that's about 20, 30, 40 times the droplet impacting?
This is experiments.
This is experiments, yeah. Yeah, so all the symbols are the experiments, and it's as far as we could get within that configuration. And the numerics I'll come back to in a second, because they helped us with something else. Yeah. Cool. So I'll leave that with you to ponder in the background. Now I promised I'd tell you a bit more about this line, which brings me back to one of my favorite topics, which is Wagner theory, which we've talked upon both this week and last week. All of these beautiful images are courtesy of Madeline, because my skill set in drawing figures does not go that far. But just for those of you who haven't heard about Wagner theory before, it's a beautiful matched asymptotics framework in which you use essentially inertia as your main ingredient on top of geometrical features, and throw away typically elements like viscosity, surface tension, gravity, in order to give you a very good description of what happens to the splash sheet at sufficiently early times. So more detail on the structure you can see here, but the only kind of thing I wanted to tell you that's relevant to us now is we can get very good information about what happens at the root of this jet in terms of where it is, what the local velocities, pressures are, what the thickness of this jet is, so we can help ourselves to a few ingredients that if we were to have experimental and computational results, we could bring everything together to get another compact predictive formula to help. Was that subtle enough for foreshadowing? This is exactly what we're going to do next. So we've inspected for the various viscosities in the pool, different centistoke values. We plotted the maximum pressure values as obtained from the simulations. And what I'll try to convince you of is that if you use a suitable adaptation, you can collapse them into one nice curve that then you can use into an adaptive model. So from the Wagner theoretical framework, we can read off essentially where the contact line is, where the root of the jet is relative to each problem set up. And from there, we can extract the pressure at that point. So I have something that I'll call pressure max Wagner. We know where it is. It happens at the time of the jet ejection, and from there on, it decreases slightly moving forward. But we have an expression for it that depends on a few key parameters that we know. The other thing to note is, in most of the problems I've worked on, or at least for that particular law, it was used for static surfaces, solid surfaces, or small adaptations of it. We, of course, looked last week, and the diagrams were drawn for liquid-liquid impacts as well, so we know we can do other classes of problems too. But in this one, what we want to do is modify the velocity such that it's not just the impact velocity, but it also includes the interface velocity from the equation that I showed you earlier. So we have an expression of this moving front from the previous study, and we want an adapted interfacial velocity to basically make a small modification to this model, but otherwise use the same information about pressure in order to arm ourselves. This is actually the idea, and kind of the fact that you do have a threshold beyond which in this pressure you can predict when it would be a good indicator for splashing happening, like what is your threshold value, comes from a really nice paper from 2016, which is called "It's Harder to Splash on Soft Solids." I like papers that have everything in the title. But in that case, you get a nice set of curves collapsing again, and this idea of a threshold pressure beyond which you may expect splashing to happen based on the analytical formulation. So you can play this game. You can adapt everything because you have information now coming in through this V bar, which is our adaptive interface velocity, which you remember contains density ratios, viscosity ratios, so it does pull in information about our problem. You can basically use an equation of this type to get your threshold impact for splashing. So I think what I was trying to say kind of briefly, not quite so briefly as I would have liked, is that this line comes from that formula. So basically, it's not perfect as you can see. It undershoots or overshoots in strategic places, and it does rest on a few assumptions and maybe strong arming a few coefficients in as well. However, it is a compact formula that seems to be quite robust across, several orders of magnitude in viscosity ratios, which we were quite happy with. I'll jump back now to the formalism in question. And the only other thing I wanted to mention about this problem was, because now we have the computations validated to a point where we are happy with them, we can start asking questions of the type, if we do have a splash sheet forming, where does the liquid come from? Does it come from the drop? Does it come from the pool? Does it matter with respect to viscosities? Which is when I'm going to come back to the question I asked you. Why do you think we got that unsplashable droplet impact? And the clue is in this picture in some sense. Something happens to the splash sheet emerging in terms of its constituency, if you will, that makes it a particularly interesting case. And to spoil the fun, basically what happens is that happens to be the sweet spot for which you get just enough deformation of the viscous pool. It looks like a crater. There's some nice supplementary movies that I can show you at some point if you're curious. But basically, intuitively, you get strong deformation from the pool. That means that splash sheets coming up would actually be quite hindered. Gravity doesn't play much of a role, but they still have to go uphill. And at the same time, the composition changes. It starts drawing in fluid from both regions, and it seems to basically dissipate just enough energy such that it's not able to overcome the multiple effects coming through together. If you get impact at lower viscosities, you'll notice much of the splash sheet comes from the pool. If you get impacts onto a very viscous substrate, much of it comes from the drop shattering. This is the in-betweener where basically you put strategic amounts of energy in each place and you're not able to get enough to splash. Maybe I should have shown you, and I've been bad at this, a key movie that hopefully kind of paints a picture of what I want to say as well. These are different viscosities, and this is the 1 million centistoke one. And you'll notice as the viscosity increases, the speed and the violence of the situation also increases as well. So this was the case for which you primarily get droplet fluid, and I'll jump back here. For the other one, you get fluid coming from the pool. But since we have these capabilities now, hopefully these are useful ingredients. For example, if you remember the aerosolized droplets coming from the impact onto oil slicks, this may help us try to ascertain how much oil is coming into those respective secondary droplets. And I wanted to get slightly closer, and this is something that just came out a couple of weeks ago. What happens now, so everything I've shown you was for a deep pool. It had different viscosity, different density, different properties and so on, but it was always a deep pool. What happens if instead you have a thin film? So experimentally, or numerically first, you get this configuration. So you have droplet of water, say, coming onto an oil-covered pool of water. And you see there's now two interfaces. There's an upper interface that may do things similar to what we've seen before, but there's a lower interface as well, and there may be a mechanism for interaction depending on the thickness of the film. And experimentally, somewhere, this is this one, this is this one. Yes, we can get information about the bottom, but it's very hard to get information about the top. So I'll show you again. This is again the under interface side. You can get top droplet type animations. You can get bottom from the bottom so that you visualize the underside of the pool. It's very difficult to get actual thickness information, which is why the simulations help. But with this in mind, I'll just show you a couple of slides. The velocity of the upper interface that used to be about 0.5 before, if it were the same fluid, so if no oil film was present, you'd expect to get this value. If it were a deep pool of oil film present, based on that equation I mentioned before, you get this value of about 0.32. Depending now on the thickness of the liquid film relative to the drop, you get to see essentially a trend where initially you start off from around this value of 0.5. If the film is very thin, it's non-noticeable. It's as if almost it's the same fluid type of situation. However, once the thickness of that film increases, you get gradually close to the deep pool theory, and it turns out that around the value of that film thickness being about 1 diameter, it's as if it were a deep pool. So I like the type of questions when you do asymptotics, how thin is thin, or how thick is thick in this case. This gives us a bit of a metric as to when do we need to consider the actual finite thickness. The other interesting feature here is you'll notice this is kind of outside of the error bars as well. There seems to be a little increase and then a decrease again. The way we've rationalized this, but I think a better model or a better way of structuring the idea might help, is what happens is if it's a sufficiently thin film but not too thin, you get the droplet pushing onto it. If you think of it like a spring, it gets compressed. The lower interface then moves and drags everything else with it at a speed that's just marginally quicker than the top one. We've inspected velocity fields and other things inside of the simulations, and that seems to offer us some indication, but I think we need an actual rigorous model to further that idea a bit more. And finally, yeah, we can inspect then a whole host of, these are different symbols for different centistokes, so like different viscosities of the oil, and you see what always happens is, for reference, we have the line from that predictive formula. So provided that the film is sufficiently thick, you always land there. But there's otherwise some interesting non-monotonic dynamics happening. You always get this slight bump that I mentioned that manifests itself a bit differently from different parameter places. But all in all, you get a start from about a value of 0.5, and then you converge, and you have access to the full set of behavior in between. So yeah, this is the story I wanted to tell you. It required in the order of, well, I started 10 years ago, but we started working in earnest with Ben and having proper experiments and computations about 5-6 years back. We've burned a few clusters in a few places, 3 to be precise as well. But that's the story I had in mind, so thank you very much for indulging me.
Thank you very much, Radu.
For your talk. I understand your argument for no splash. I'm still not totally. I would have expected that maybe at very high speed you will have what people call prompt splashes, that means very small droplets. Maybe you don't see them in the experiment?
That is correct. I think the pool, as the drop hits, deforms so much that it's difficult for the camera to see things that may be shooting off if they're very small prompt splash style droplets, and yeah, numerically we can capture them.
Somehow prompt splash and regular splash are not so easy to distinguish. So, but yeah, I would not be surprised that you may have this type of flashes before.
We'd probably need a camera from above or a particular type of dye, maybe with some fluorescent capabilities in it, and I think you can crack it. But yeah, I like the mystery side of it for now.
No, it could be some kind of a singular effect which makes that the critical, but I'm not sure it's that.
Yeah, thank you.
Thank you, Radu. You just spoke a lot about viscosity ratios and density ratios. You didn't really mention surface tension ratios from the droplet and the pool. So what would you have different surface tension? What do you think you would see in those kind of cases?
Yeah, I mean, just to preface it, density ratios you could change up to a factor of 2 with the various fluid choices. I made a bit of a fuss about the viscosities because that's the one we had full control over. They do have 3 different pairwise surface tension coefficients. So we picked up the actual kind of fluid values. We could change them. I think actually numerically that might be something interesting to explore. Practically speaking, because many of these values go, again, within a factor of 2 or 3, we thought that especially for the early times and for the higher speed cases, I think we banked on it being a more secondary role. I think if we wanted, for example, to monitor something like impact, spreading, and then retraction, a capillary retraction into a liquid lens type of situation, which is actually often our validation case. In that case, changing the surface tension might have quite dramatic effects. The other detail that might be noteworthy here is surface tension will likely affect, will definitely affect the contact angles in a very delicate way. The numerical methods in VOF and in this particular formalism struggle for very small or very large values of contact angles. So if you get sub 30 degrees or above 150 degrees or so, you start, for example, getting things stuck artificially. So my feeling is you can operate within a window and get some nice insight, and then there'll be a point of uncertainty beyond that where you're not quite sure what you get and if it's reliable.
Thank you.
Thank you very much, Radu. I just to remind to all participants that Radu did lectures last week ago, and it's about 4 or 5 hours, and all the records will be available online once after it was will be processed by Isaac Newton Institute. So many details about asymptotics, about numerics could be found there. But I also have a question, because to me the JS and Basilisk, they are famous because they are well-traced interfaces. Right? This is a difference from many other softwares. But on the other hand, in physics, it's possible because of that shear stresses that the fluids became miscible. Right? And what to do? Because I don't remember any papers, any research about impact with the mixing after that. So any ideas?
There is a way to study this. So one thing we've looked at ourselves historically as well is, for example, you could put in an artificial tracer inside your target environment, like say just a drop. So you can have the drop and the pool of the same liquid, say water, and just add an artificial layer on top that is a different color function that's passive, if you will. And you could, in principle, monitor then what happens at the point of impact between two different regions with miscibility in place, and you can see how much of the tracer that was originally in the drop, say, would go inside of the pool. You can have it inherit the properties of the fluid region it's on top of, say the drop. You can also add further diffusive aspects to it. Ultimately, I think in many cases, if the miscibility itself is the target problem, I think one needs to be quite careful about the physics and the detailed algorithmic setup. But yeah, there are some kind of levers we can pull in that direction. And of course, I think in that case, you'd have to match surface tension coefficients quite carefully as well, depending on whether you want that or not to play a role in one's hypothetical internal interface. But it's something we can look at. It just, I think it may be quite regime delicate, which is okay. That's why we're here.
Okay, I think we should wrap up at that point. Let's thank Radu again.